In problem number 15, we're kind of doing the reverse of what we did in problem number 14. So in this case, we're given a Riemann sum already set up in infinite form that you could evaluate. And we're asked to put this back as a definite integral instead. And this will be much easier to solve that way, obviously. So what we need to do is recognize we have the limit as n goes to infinity and our sum I equals 1 to n. So this is already in the Riemann sum form. And these two things essentially become the integral sign when we switch back to being a definite integral. So as the sum of the rectangles goes to infinity, we just integrate the function. So what we need to figure out here is what is the function we're integrating, and over what interval are we integrating it. So we have two pieces of this function which you should always be able to recognize. We have 1 over n. This is our width of our rectangles, which means this is the width of the interval divided by n, because, let me write that over here, as b minus a over n. Remember that the width of the rectangles used in Riemann sum form is always however wide your interval is divided by how many rectangles you have. Well, the amount of rectangles we have is n when we're doing this type of problem. So that means 1 must be the width of the interval. So that tells us that whatever our interval is from a to b, we know that that distance is only 1. That doesn't tell us what they are. We just know that the distance is 1. The other part of this summation, cosine of 2 plus I over n, this is going to tell us what our function is. So if you remember from problem number 14, when you have the term a plus I delta x in your Riemann sum, that tells you like where the x is in the function. Notice we have something that looks kind of like that inside this cosine. Our delta x in this problem is 1 over n. We already determined that. So I times 1 over n would just be I over n. We have that right here. And we have a 2 that might be a. And I say might be because when you have a number added in here, that could just be part of the function. Or it could be that that is an a and that's where the function starts. It might sound kind of weird at first, but both of those ways are correct. And you'll see that in a second. So first I'm just going to assume that that 2 is actually a. Therefore, this whole expression is right here, which means that this is just x. So if I assume it that way, that means that this is just the integral of cosine of x. The width of my interval was 1, but I've determined that a is 2. A is where this integral would start. So that's from 2 to 3. And therefore, this whole expression that up here is equivalent to this. The other option, well, actually, there's an infinite number of options, but the easiest other option to see is, let's say that this 2 was not a. That was part of my function. Like my function was cosine of 2 plus x. That's entirely possible. In that case, I could assume that my a is 0 because there's nothing else added to the I over n. So therefore, if that's my function, my interval could go from 0 to 1. This is also an acceptable version of this. And if you take a close look at it, these two things are actually the exact same thing. Because look what's happening here. You're going from cosine of 2 to cosine of 3. Here you're going from cosine of 2 to cosine of 3. Maybe more precisely, when you have a plus 2 or a 2 added inside a function, remember that that's a transformation. That's a shift to the left 2. So this is saying we're taking our cosine function and we're shifting it to the left 2. Well, look here. My x values that I was concerned with are 2 or 3, 2 and 3. I shifted those to the left 2 and got 0 and 1. So these are exactly the same thing. I mean, it's not even like they're different things that kind of look the same or different ways of evaluating the same function. Like these literally are the exact same thing. So either of these would be an acceptable way of rewriting this Riemann sum, either one. it's likely on your test that they're going to test that you know how to do that by only putting one of these on here, and it might not be the one that you immediately went to first. So you need to know how to be able to recognize two integrals that are the same. So now let's actually evaluate the integral. Again, it doesn't matter which one you use. I'll just use this first one over here. So if I want to evaluate this integral, I need to take the antiderivative of cosine. The antiderivative of cosine is sine x. And I'm evaluating from 2 to 3. When I plug 3 and 2 into sine of x, I don't get any, those aren't any specific angles that I would know. I just leave it as sine of that. So this would be sine of 3 minus sine of 2. It's the exact, that's all you can do with it. That's the exact answer. You would get the exact same thing if you integrated this one, because the antiderivative of cosine of 2 plus x would be sine of 2 plus x. And if you plugged in 0 and 1, you get the exact same thing. So just keep in mind that while you need to remember that a Riemann sum has a b minus a over n term, the width, it has an a plus I delta x where the x should be in the function. That a may or may not be the number that's there. As long as you transform the function appropriately, like shift it left or right, it doesn't matter which one you do, and they're the exact same thing.
The Teaching Center, UF's Learning Resource Center.